sir. Live stream is started.
Okay.
I think we can start. People will join. Nearly 20 people are there.
But that sound keeps coming. Cut. When
Yeah, we
joining.
need to cut out the login tone, I think. Good.
All right. Is the full screen all right, Page?
Yes, sir. It looks good.
Shall I start?
Sir.
Yes, sir. We can start. It's 8:05. I think we can start.
All right. Again, good morning to all of you for this fourth day session. Today's plan is I'll be covering some more material, trying to bring in some of the loose ends and tie them up and in the first hour. And then in the next session after that, after the break, I'll cover a lot of case studies, as much as I can from different areas and different works, both from outer sources from the work which has been going on here. We did in our own labs over here at the University of Mississippi. Our students do those work and all that on modal analysis. So that's the plan. Anybody, any questions and all that? Something which I can clear quickly before we start? Anybody raise hands, Dr. Prasad? Anybody?
No, sir.
Okay.
Yeah.
Then I'll proceed. Again, this is tying up a few things, okay, which in transducers and things which I may or may not have covered, but re-emphasizing is important. Especially, we are focusing more and more on the impact testing because that's the one more likely most of you would be doing in your work. So there are other exciters also there and all that. Much more involved techniques, but this is the most common one. So let's focus on some of the aspects of that. Most popular excitation techniques used for modal analysis is the impact or the so-called hammer excitation. Okay, the waveform produced by an impact is a transient. Okay, it's a transient in time domain. It's sudden transient. Okay, which has the finite width associated with it, and the shorter the width, sharper, the longer the energy content in it would be in the frequency. The spectrum for that final time domain in the spectral domain, frequency domain, log magnitude, is continuous with a maximum at the 0 hertz and after some time decaying amplitude as the increases. So the spectrum has a periodic structure with zero force at frequencies of n over t intervals where n is an integer and t is the effective duration of that transient. Okay, it goes on. But what's the useful range that you can test the frequencies is typically taken to be at about 10 to 20 dB drop off at this point. So typically up to this point of the frequency is what you can expect the energy, enough energy content of the impact would be there to excite any of the natural frequencies of the structure that you are testing. So, the duration and thus the shape of the spectrum of an impact is determined. What factors will dictate this, whether to make it large or whether to make it sharp, is determined by the mass and the stiffness, mass and stiffness of both the impactor and the structure which it is impacting. For a relatively small hammer used on a hard structure, the stiffness of the hammer tip determines the spectrum. Okay, so that tip, the tip of each hammer is a tip. the hammer tip acts as a mechanical filter. The analogy is not strictly correct since the tip does not filter out energy. It determines the frequency range. Okay? The hammer tip has a mechanical filter. Selection of the tip stiffness enables the cutoff frequency to be chosen. So this is the tip of the hammer. You can remove it. It's screwable. Okay. This is the actual mass, actual hammer head, and there is a force transducer in between the hammer and the tip. The force transducer collected through wiring, and this over here, and a stiffening member. Impact hammers are constructed by adding a force transducer to a hammer and adding a stiffness controlling element to the end of that transducer. Okay, the stiffness, you don't want that to be losing the stiffness. And you should be careful that the measured force is the mass of the impactor behind the piezoelectric disc of the force transducer. Okay, multiplied by the acceleration level, mass times the acceleration, how fast, how movement, your movement of the impact together will give the amount of force which is going into the structure. The true force exciting the structure is equal to the total mass of the impactor, including the force transducer and the tip. This is the total mass multiplied by the acceleration due to the impact. The true force is the measured force from multiplied by the ratio of total mass divided the mass behind the transducer piezoelectric element. Now these things can be, they'll provide you the base hammer head, accelerator. This you can change to whatever force transducer head. This is changeable. I mean, this usually with the hammer head, they may integrate it sometimes, and they'll give you extra masses. You can go on adding, screwing on more and more masses to that. And that way you can be constructed with weights ranging from a few grams to several tons, which together put together the spoke covering the frequency range anywhere from 0 to 5,000 hertz with the smallest, and 0 to 10,000 hertz with the largest hammers that are available. Okay, so again, you see, notice here what happens if you had used a steel tip over here head, you would have got a sharp spectrum in the time domain, sharper as compared to the other, which would have given you broader range. You see that over there up to 5K like that when the drop off takes place and all that. Okay, so and then if you use the plastic head, then this is the drop off, and then a rubber head would be something like that. So decide if you are fine tuning between 1000 hertz, you may want to go on the type of delicate instrument, delicate material you're tapping and all that. Use this head, okay, and something which you can withstand more hard impact. This, so there are things you consider, and range and pay off back and forth speed. Advantages, only a few averages are needed. Again, you never ever impact and then take the data and coherence one, run with it like we talked yesterday. Okay, you got to keep impacting, and the biggest and greatest instances where you will get bad data is the double hitting if you try to hit with your arm entirely rather than a wrist impact, which would avoid double hit. So no elaborate fixtures are required. There's no variable mass loading of the structure. This is a particular advantage with light structures. So changing the mass loading from point to point can cause shifts in modal frequencies from one measurement to another. So the same mass you're impacting. The variability of the impact is the tendency to hit faster or slower, which is taken into account in the averaging process, right? So things like it is portable, very suitable for measurements in the field, relatively inexpensive compared to a shaker and all those setup and all laser vibrometer and all the. Of course, they are pickup devices, but compared to a shaker, this is for sure. Some disadvantages, like we talked before, the high crest factor, sharp crest factor makes the technique unsuitable test systems with nonlinear properties, since the nonlinear behavior will be provoked. To apply sufficient energy to a very large structure, very high peak forces might be required and the structure will become damaged locally. You don't want that. to hit hard. Signal is highly deterministic, and the force level only varies slightly between overload and trigger, underload levels, okay? This means that no linear approximation made for non-linear systems. Due to the deterministic nature of the signal, the coherence function cannot show either leakage or nonlinear behavior. The spectrum can only be controlled at the upper frequency limit, which the technique is not suitable for zoom analysis if you are doing and things like that. Impact testing, again, coherence function. We said impact is very important to check. Will show perfect value of 1. If it shows a perfect value of a coherence within that frequency, a 1 value like over here, anywhere which is showing over here, then unless it should at each peak, unless there's what's called an anti-resonance, where the signal to noise ratio is rather poor, then it will drop off. You see that? So that's not a pure, it's anti. No particular attention needs to be paid to this. Taking a number of averages should make the FRF curve smooth. Okay, and for noise at the should make the FRF for noise at the output choose. If you want noise created at output, choose the H1 factor. Remember H1, H2, the provisions are there will take care of that. The person conducting the test impact the structure in a scattered way with respect to point of direction. It should be as perfect, as close as perfect perpendicular to the hitting, not in angle. This should be minimized so that the coherence is higher than 0.95 at the resonant peak. You should check at the resonant peak. What's the value of the coherence? What's the value of the coherence? Okay. If the impact point is close to a node point, the coherence may be extremely low, 0.1. This is acceptable, however, since the modal strength in this peak is weak and not important for the analysis. So they go together in impact testing. Again, window testing briefly before discussing for impact, we'll review two important relations. Time-frequency relation. Data can normally be presented in different domains, time or frequency. The same information is given, but it is simply a form of representing in a different format. Remember that a wide event in one domain is equal to a very narrow event in the time domain like this. Short pulses, short, sharp pulses have a wide spectrum from 0 to up to very high frequencies. A continuous sinusoid has only one line. Suppose you input that as a sinusoidal sweeping function with a spectrum, with an exciter, sine, straight line. You see like this? A sharp resonance rings for a long time when excited. That ringing sensation, okay, will be there for a sharp resonance. Now this introduces truncation errors and leakage and things like that. When the observation width is limited in one domain, like you cut off over here, the record has been truncated, which is what is doing in some of the applying some of the windows, and a corresponding leakage is introduced in this domain. If you had a continuous spectrum, it was like this. You truncated it off like as if you are breaking down the ringing and all that. It adds on an additional damping over here, shortens and shows some of the other seeping in. So if you try to measure a sharp pulse using instrumentation which has insufficient bandwidth, then this pulse appears to be broader. Again, you should choose in a sufficient bandwidth and all that. When a decaying resonance is measured using an observation time shorter than the complete time period over, that also introduces that leakage. Instead of really being sharp like this, it introduces the additional damp and maybe a second peak, things like that. Leakage introduces a nonlinear error related to the record length of the discrete Fourier transform. This is an inherent property and not related to the implementation. Okay, so those are some of the issues which you can work around using some other methods that we talked about. The transient window, duration of impact is usually very short compared to the record length. So special consideration must therefore be given to the applications of windows. It is the force signal during the period of impact which is of interest. The remaining signal is noise. This could be electrical noise, a vibration in the hammer itself after impact. So this window, transient window, is used in that case, for taking care of those. This takes the data unweighted during the period of impact and sets it to 0 for the remaining period. So only during the impact and takes it into consideration and removes all other things over there. So when we look at the time history of the impact force, negative cases, sometimes you are observing the negative signals and all that over there when you do measured signal. And this short ringing is a correct representation. So you can use that to take care of that, focus on that. Another thing is double hits, which will occur. If the hammer is too heavy, the structure, first of all, if it's too heavy, the structure will rebound. You don't have to do double. It may rebound and hit back, which is essentially like relative movement of the two, which causes a double impact. The occurrence of double hits also depends on the skill of the experimentalist. A double hit cannot be used since the spectrum will contain zeros. See, if you go on, if there are double hits, you'll see like this. The spectrum will look drop down, drop down, drop down, drop down, and very bad. You see this? Okay, true FRF and the measured FRF function would look more like this. Okay, double hits cannot be compensated by using transient window, and any frequency response functions measured with a double hit will be erroneous and must be excluded from the data set. If you see something like that, don't take that into the averaging constraint. Okay, repeat the test, number of average. That's the transient part of the input. The response window, output. The response is a free decay typically of all the modes. If you excite the structure with a hammer, all the resonant frequencies are excited, and each one of those resonant frequencies are decaying, and usually the fundamental modes take a longer time to decay. The higher modes take shorter time to decay. All of them and then dying down. A combination of decays is taking place. If the structure was lightly damped, okay, giving sharp resonances, okay, for the impacts, narrow in frequency, broad in time. This is broad in time, narrow in the frequency, lightly damped structure, sharper and sharper, no damping, this should go up to infinity. But as you have some damping, lightly damped, reasonably sharp. As you see more and more damping, this will become broader. Okay, I'll show you some examples of the work I did showing those pictures and all that on a spectrum analyzer for a particular case pretty soon in the case studies. Okay, truncation, the one when you apply this response window and you truncate off the data, okay, resulting in the observed resonances being too low and too broad. Okay, a heavily damped structure, lightly damped structure, heavily damped structure. If you introduce this exponential window and made it come down to 0, there'll be a difference. The true was this, but the measured, the extra damping added in that exponential decay, you forced it to die down, created that artificial this thing. Okay, but sometimes it's necessary evil, because it will go on forever, and the anti-aliasing and these things come into play. Okay, a heavily damped structure, for example, where the response decays very fast already. Okay, if the force record length is much longer than the decay time, there will be a poor signal to noise ratio, and the measurement will be compacted more by noise. Okay, the exponential window will handle both situations equally well. It's a function of the W response with time e to the power of minus t times tau, which adds decay to the response with the following effect. Okay, for the lightly damped structure, the response is forced to decay completely within the record. Okay, the observed effect on the measurement is the resonance becomes too broad sometimes, or the apparent damping is too high. Apparent, not the real damping. This is apparent, introduced. A damping correction can be easily be applied at the post-processing. So it's not that horrible. Okay, if you really want to do, force it, get a good data, and apply that, compensate it with whatever that force thing was by a post-processing stage. There are instrumentation facilities which allow you to compensate that decay actual and what you did and make a provision. For the heavily damped structure, the noise is attenuated by the window. A damping correction is not required since the natural decay is generally much faster than whatever window function has been applied. So, for most of your work, you would be applying these windows, and if damping is a crucial for your work and all that, again, damping can be introduced to any and every. We went through that over my lectures. But one of these and the future of adding additional damping, instrumentation, aliasing functions, and introducing windows adds another factor of damping. So if you do need to take a reasonably correct value as opposed to what the thing is by applying the window, do that correction and see how that looks. Okay, so the provisions are there to account for that. Again, here gives a good comparison between the excitation forms. Besides these three excitation forms that we discussed, there are other types. Chirps, sudden chirp, fast sine chirp sweeps, fast sine sweeps, sine function given burst and then stop, then again burst and stop, burst, which combine the advantages of amplitude control from sinusoidal excitation. You can control the amplitude with this, with the speed from the wideband methods. Periodic random and burst function. Okay, this is sine. It's a specified but random, burst random. Both take advantage of the random amplitude and phase for the randomization of any nonlinear behavior, and their periodic waveform avoids leakage errors. So if you want to avoid those and no more, then going for this. Cost, time consuming, more costly, doable. Random repeated impacts for low frequency work, time records lower than the 2 second, improve the signal to noise ratio. This uses the same analysis technique for the random waveform, but maintains the ease of hammer. So these are some things to consider. Again, it gives you for each one possible sinusoidal, random, pseudo-random, impact, multiple impact. What are all the pros and cons? Leakage. What is a linear approximation? Crest factors. For example, impact crest factor is poor. Spectrum control, zoom analysis, coherence. All these plus and minus. Before you, or every once in a while, you're required to, the supplier of your impact hammer would sell you a calibration sheet and a form, and it's essential that you try and verify that before you do some serious testing and all that, you need to check the calibration yourself. You can do it, okay, very easily. Most commercial transducers are supplied with calibration certificates, but a calibration test before every mobility measure is strongly recommended for the following reasons: to check the integrity of the transducers and to detect any errors in the cables and connectors, conditioning, and analyzer. To check that all gain, polarity, and attenuator settings in the system are correct. In a long measurement chains, one setting can easily be forgotten, okay? To check that the repair of transducers being used are matched in the frequency and band of system. So how do you calibrate the entire system is to measure the mobility of a simple structure. The easiest structure to use is some mass, some known mass, okay? Some perfect, as close as, you weigh it and divide it by a mass, okay? You weigh the mass, not the weight, okay? You take that mass and known mass, and from Newton's second law, the force is equal to the mass times the acceleration. So you take a mass and you apply a force signal to it of known force, and the acceleration both are measured. It's seen the accelerance by definition is accelerance per unit force. The accelerance function is inversely proportional to the mass times acceleration 4. So any frequency, the acceleration has amplitude 1 of mass and a phase of 0 degrees. So you do this and check it, and the mass that you arrive at should be equal to the mass that you apply. If you use this shaker, a known force, or an impact hammer with the force given by the transducer and the acceleration, this has to be satisfied. This should be equal to that mass. So a known mass suspended so that it moves in only one direction with an accelerometer to detect the motion can be used for either impact or vibration excited. This gives a ratio calibration ensuring correct mobility measurements rather than an absolute calibration. For this purpose, even a handheld held mass is adequate. Okay, you can take a mass and put it in your hand and then impact it and check the response and all that. That's okay. Along this, they are again calibrating to check. Again, a few comments on impact calibration. If the calibration mass is considered to be absolutely rigid, which is not really true, in the frequency range of interest, the force and acceleration forms are equal. Okay, ideal calibration. Okay, if both a force window and exponential response window are used, the apparent sensitivity of the response is less than the theoretical response. This is due to attenuation caused by the exponential window, but nevertheless, the correct sensitivity calibration for the complete measurement chain. Okay, so I have, I think, covered most of the instruments and the windowing functions, and as much as we can to try and be able to prepare you for doing a modal analysis test. Then there are some you got to, before you jump in, like you said, and start doing off some testing and all that randomly knowing. There's some things you need to pay attention to. Okay, to issues. First of all, solving noise, vibration, failure problems in mechanical systems can be described by a four-step process. You got to chalk out a plan, and the plan is consisting of well-defined plan consisting of these, say, four processes. First of all, characterize the problem, measuring the frequency characteristics of the structural response. Okay, identify the structural resonances. Now, is it because of a forced vibration, some external force causing some sort of a sharp spikes which you believe are resonant frequencies, which are not true? Okay, is it because of a forced vibration coming? If it is, try to reduce the. If it is, or if it's not, either way. If it is some, usually there'll be some forcing, some motors and all that. First, reduce the force level or isolate the structure to do that. But then, if we suspect if neither of them is causing, then some resonant conditions are taking place, then go to that. If that's the case to resolve, then you have to perform a modal test to find the deformations at the resonant frequencies. Then after having done all this, what do? There's something you need to do. The whole purpose is to try and resolve certain issue of either this type or this type. So what do? The chances, the things available at your disposal are to modify the structure, either move or attenuate objectional resonances. If any of these resonances are coinciding and it is creating problems, either move or attenuate. Means if you cannot move the resonance, sometimes condition, attenuate, bring it down, reduce it. How do you do that? Add damping. Okay? Attenuation. If it's unavoidable, then additional damping parameters, not too much, overdo it, but take some look at it and see whether that would help. Shift resonance, move the resonance condition to a higher frequency. Shift the resonance to a lower frequency. Both are possible root of in a very simplistic form. Those resonant frequencies, natural frequencies, are proportional to square root of, or proportional to K equivalent over M equivalent. On the top, K stiffness and the mass at the bottom. And what it tells you is that resonance can be shifted by increasing the stiffness or decreasing the mass to move the resonance to a higher frequency. Be careful that it doesn't hit some other forcing condition there. Or the other way around, make that resonant frequency lower by less stiffening, put softer springs or something on the K part to take care, lowering the stiffness, and at the bottom, increasing the mass if it's possible. Either which way you move that away from the condition. And one thing done with some systems which are fine-tuned single degree of freedom systems are what's called a tuned vibration absorber. It's a lumped parameter spring system is defined. At the bottom of it, attached to the mass, they introduced a second single degree of freedom system with a spring and a mass approach. and it's a resonance, and under a resonant condition, it will start the secondary mass, which is smaller and less effect spring than the other one, will absorb the energy, and essentially it will become a 2 degree of freedom system with two modes which are swept away. If you look at that analysis and all that, it will show two at a broad moved away from the resonant condition, and so resonance does not take place. So that tuned absorption, a lot of these are there out there in your machinery and all that they're introduced. They're especially important when the condition of resonance is taking place at a particular this thing. It is always taking place, and be careful that the other two shiftings do not excite some other frequencies. So that's one way out. These are all the things you can do to try and take care of this and test it. Traditional methods for altering the physical properties of structure requires judgment and experience. As you work through all these things, it's a vibration problems are always trial and error process involving costly testing and retesting. So again, talking about each one of these step by step, first step is characterizing the problem. Measure the, this is where the operational data comes into play. Once you put the two accelerometers on a system and just let it run whatever forcing condition and all that is taking place, you start seeing the output ratio of those as some sorts of like this, okay? Some looks like this. So measure the operational data in order to identify the dominant frequencies. Look at this from the operation as it is under extraneous condition. There's no force transducer here. You're just using the two accelerometers to get relative quantities at various, and that will pick up all the data. This data is necessary to help determine if the problem is due to a forced vibration or a resonance condition. So something happening like that, suppose you notice that under those circumstances, at some frequency, let's say, what is this scale over here? Maybe this is 10. It says response is caused by a large excitation force which drives the system at 10 hertz. Something is forcing 10 hertz, you see a spike. It need not be a resonance of the actual structural resonance, either this or is it a structural resonance at 10 hertz excited by a small excitation force? A very small excitation force is sufficient to excite a natural frequency and cause a very sharp spike. So that's the modal analysis part of it. Otherwise, very large excitation forces will also cause some, it's not a resonant condition, but it will force some response pushing the spike. So you got to distinguish between these two, okay? So once you distinguish that, identify, you want to know what the structural resonances are compared to this, okay? Then you do measure frequency response function at several points on the structure in order to identify any structural resonances near the problem frequency. Correlating this data with the operational data aids in determining if a problem is due to forced vibration or a resonance condition. What happened here? You see around 10, there is a spike, and here also you see, I hope so, I don't know whether this is as per the scale 10. If you see these two, it looks like yes, this is more of a the structural resonance than an external condition, unless there is some forcing, some force, large force at that turns. Any one of them could cause this. In this case, it is matching that. Excuse me. Okay, so you got that. That's how you identify. Perform a modal analysis. Then at that part, you want to see completely quantify the dynamic properties at that point, frequency, damping, and mode shape of each important mode of vibration of the structure. This data forms the basis of a modal model of the structure. It shows you that at frequency 10 hertz at a damping of 2.1%, that's 0.02, excuse me, zeta damping ratio, loss factor is 2 times the damping ratio, and this is the modal pattern of that thing it is showing. You got the data. Now what do? Modify the structure. If that is the case, resonance condition and all that, then you got to do something in order to control a problem that is due to a structural resonance. The structure must be physically altered or the excitation removed. Those are the two choices available for us. The only way to alter a structure is to modify its mass or its stiffness or the damping properties. Therefore, modifying a structure to control a resonance is normally a trial and error process involving testing and retesting. Traditionally, when an engineer wanted to make a mass, stiffness, or damping modification, he had to rely primarily on his engineering judgment and experience. Okay? Adding damping to the structure so that it reduces the response at resonance. Okay? And modal analysis helps you to show where the damping treatment can be added to have the greatest effect. This is the key. Once you know, there are ways and means of applying the damping, but where do you put it? Not anywhere on the structure. Okay, you will know where to put it only when you see the modal patterns and this things like that. Then it's not just because the largest deflection is at this end, you add some damping over there. That's not the key. It's more to do what's called strain energy. Okay, especially the so-called viscoelastic damping treatments that I work with and things like that, which I'll talk in my case studies. The damping treatments and things like that should be added to where the so-called strain energy density is the maximum. Okay, at that point, if you apply some treatment, then you will see that that peak, whatever, has dropped down effectiveness. If the location of application of that damping treatment is done correctly, then it will show, if we do the analysis on that again, at resonant condition, the amplitudes of those have dropped down like this. Okay, and the only way is the mode shape pattern. Looking at the mode shape pattern, looking at the points where that particular frequency in the modal pattern is taking place, and trying to find out from the maximum strain energy is taking place, and applying these steps, at least the viscoelastic or anything else, any other physical dampers or things at that point over there will effectively produce the desired effect. Okay, or shift the resonances to a lower frequency in order to avoid the excitation. This is the original this thing, and you don't want this. You want to shift it to lower side. How do you do that? The choices are relatively simple. Increase the mass, or decrease the stiffness. K over M. K over M. K in the numerator, M in the denominator. So reducing K or increasing mass symbol will shift so that it affects the mode of interest. Okay, it will move down. Be careful in the process you don't hit in the resonance mode of interest, or shift the resonance to a higher frequency. Okay, if possible. Sometimes one or the other is not possible to remove mass may not be possible for a system. Okay, then increase the stiffness. Okay, if possible to both, fine. Okay, just don't think by changing the material and all that things will take place. Okay, the concept of root of K over M for a resonant frequency will remain the same, whether that is made of steel or aluminum or copper, or because the proportionate of that modulus and the mass for those elements are exactly proportional, almost close. So it will not shift those materially unless you use exotic composite materials to replace. Okay, composite materials like carbon fiber epoxy, glass epoxy, and those have a high stiffness for a relatively low mass. Okay, their weight to stiffness to weight ratio and all that are really good. So you can achieve those with for those materials, not just by changing materials for a given structure and all that. So detune the resonance. If neither of them are possible, detune. This is the resonance peak. Okay, absorber. If you know the exact frequency, you can design your vibration. Simple. There are simple mathematical ways of trying how much of a mass and how much of a stiffness element, a small one, attach it to this. Physically attached to the mass of the original system will create. And when this first system goes into the resonance, it's tuned to so that the second system picks up all those and goes into its own state of resonance. So, and a single degree of freedom system essentially becomes a 2 degree of freedom system at that point of interest, and essentially you have avoided that resonance. So these are commonly used all the time, used in well defined systems, like machinery and all that, where rotating speeds and things like that, heavily very fixed fundamental frequencies, very clear, very defined its band, so that you move away. The more and more you can move further and further you can do, but then there's a danger here. If you start adding damping to this at this point, there are some issues and create some problems and all that. Then these things are not that effective. There are some issues. It's a subject in itself, fluid absorbers, which is a chapter we do cover in vibration problems and all that. But that's one other way available to you. Okay, and then you got to keep asking these questions when you're analyzing. How does a stiffness modification change the pole location? Pole location, damping, and frequency. How does a damping modification change the pole location? How does a mass modification change the pole location? So these are all things which you look at and work on them back and forth and all that and everything, to try and achieve what you're arriving at. Finally, testing, experimental testing. We would like to do testing and analysis all the time, but obviously they need to go to, in order to validate what you're getting, you got to do some modeling part of it and all that. So that's a combined testing and analysis. A real professional experiment model analyst would always go on back and forth doing both of them together rather than isolation. So what do they constitute? The goal is to use analytical and experimental techniques together in a way, complementary way, so that the engineer or dynamist can draw on the strengths of each technique, each of them. So benefits: to avoid the time consuming back and forth trial and error approach to solving costly noise, vibration, and failure problems in mechanical systems. A combined approach is desirable. Traditional methods of trial and error, experimental modal method. Okay, you structure changes required. It takes 4 to 20 hours. Okay, and structural changes required, no, then you're done. If you require, then yes. Then again, modify the actual hardware and everything. That takes in the 2 to 20 hours. Retest after each modification to confirm the change. So this goes on in the experimental method. Okay. Analytical model method develops some basic FEM configuration. It can take several days to weeks. Perform an eigen solution. Eigen solution is, eigen means to get the natural frequencies, eigenvalues, and eigenvectors. Eigenvectors is mode shape is eigenvector for each eigenvalue. If there are any structural changes required, no, then you are done. If you need those, modify FEM to incorporate the desired changes and feedback to that over there. How do you combine them? You combine the two together, okay? Traditionally, separately. You have got to go make them in unison. Get this, get the parameters, get the eigen solution. Modal parameter gives you the frequency and damping mode shape. Finite element will give you something. Develop a modal database, okay? Structural changes required, then use the eigenvalue modification process to evaluate what structural changes would. This is much on a paper. Once you get some data, you can see that on a FEM, on a software basis, like some of the simulations what Dr. Tezeswi showed you about. You can see what on paper, before doing the costly and expensive change completely, you can see what modification would change what parameter and all that. So this sort of a thing helps you tremendously, way more than effective to fine tune and use the eigenvalue modification process to evaluate the structural changes and feed it over there and you do. If you do, then you like it, you implement it and test it now. So once all the changes have been decided, then the modified finite element model should be run again, or the experimental model survey should be redone. Both back and forth until you see some of the more exotic industries like aerospace and all that, and even automotive industry, they all won't produce the actual structure and put it into play unless they do this continuously. There are huge, massive teams of people doing this part and lots of people doing this part. Sometimes these people, I'm disappointed with these guys who work here not knowing at all about some of the concepts and physical changes that take place, but that's unfortunate. But are they necessary? Yes. Okay. But these guys over here think they know everything, experimentalists, okay, like us. Okay. But then there are certain things which we cannot do, which can be done by implementing if it's done in a correct fashion. That's all I'm saying. We got to just blindly knowing what and all that doesn't help without having any exposure to a practical side. That's the sad part with finite element people who do that continuously for their work and all that. So again, the total picture, completely it's complementary. The whole idea is to be complementary in itself. Okay, modal testing consists of parameters, modal validation, both of these validated, then the parameters synthesis of a model, dynamic model, and in the process of synthesizing, okay, structural dynamic modification. That's a huge area, huge. It can be done using our softwares and all that in the experimental stride. Structural dynamic modification means what would happen once you get all the parameters and all that and build the matrix form. You can say by changing this element in the modal matrix or this element in the stiffness matrix, and this, what would it do to the whole structure? Then you'll get the modified data. For the structural dynamics modification, mass changes, what effect it will have, stiffness or damping. Get the data, feed it back. This also from here, forced response simulation, real world, structural response, they're all together. They are integrated. They have a role to play. Okay. And sometimes, there is a lot of issue between these guys and here and all that. Hey, if it's industries like aerospace and all that, they cannot afford to do those huge building and then realize structural resonances or things like that have occurred, which resulted in a disaster. Okay. So again, what fundamental equations is common to both and experimental analysis? You see, there are some fundamental ones when we say the mass stiffness damping. What basic information can be obtained from a finite element model? You can ask those questions. So what basic information can be obtained from an experimental model test? These are all things that you can, identify and see and all that and everything over there. So at this point, I think I'm done with this part, and when we come back, I think it's about time 9. What's the time?
Sir, we have around 5 minutes.
5 minutes. Okay. When we come
3
back
minutes.
after this, I will be exposing you to some of the works, case studies of some of the typical where these things are applied in real world, okay, real life situations, things like that. So we'll do that after the break. Do you have any questions for me? Since we have some time over here. Anybody?
Questions, sir?
Hello?
Yeah, sir, I have one doubt.
Mm-hmm.
So can you just elaborate regarding
On what?
of it and where
Your
to
question broke up, Dr. Ravi Prasad. Your question got
voice
broken.
is not clear?
Not clear. It got cut off.
Yeah, sir. Hello.
Mm-hmm.
Yeah, can you just explain about tuned mass damper? What is philosophy in that, and how to identify the optimal location of tuned mass damper in order to avoid the resonant condition?
Okay. Again, tune mass dampers is, normally we cover that in the theoretical aspects in a lumped parameter system. Usually they're designed for where it is specifically clearly known that resonance will take place only within a narrow range of frequency for the given system. Okay, so that is occurring because of a known mass and a stiffening element on that system. And knowing that frequency, there are ways and means mathematically. It's a straightforward analysis which shows you like you can physically attach to the mass, not to the other spring. Then it becomes a linear spring stiffness. Below that, usually under the table and all that, and that they'll attach a spring with a smaller spring, lighter spring usually, and a smaller mass element, which put together will make the whole system now into a 2 degree of freedom system instead of a single degree of freedom system. So what happens is, under those circumstances, when the whole system is running, the fundamental mass and spring are running, moving up and down. The secondary mass and spring will also start oscillating, and at some point of the original resonance system, the whole energy is moved on to the smaller mass in this system, and they start opposing each other at that point movement. So again, most of the textbooks will give you Danny and Inman's textbook, which I use for my class, shows you the mathematical part of it for the tuned absorber. So at that resonant condition, essentially the frequency, the spike will now move away into two separate frequencies on either side. And you can make it much broader, or you can move it by narrower by the ratio of the mass of the tuned absorber to that of the original mass to the ratio. All these go into effect to move those frequencies. So it's a very common usage of this tune. One other interesting things, I don't know in your country, in India, whether we see that all the time in this huge wires. You see cables and all that, electrical cables and high voltage tension systems when you go at a freeway and all that. They have also a similar concept of like a dumbbell shaped things somewhere along the line of that thing attached. Okay, small dumbbell shaped this thing. Those are tuned absorbers actually. Okay, they are a small system built into that cable and attached to the cable, so that the cables also will, due to gust winds, just like that Washington Narrows Bridge movement and all that, at some frequency, forcing frequency, those cables have a tendency to go into resonance. So that tuned absorber will change that condition. The small dumbbell shed, which has the small mass and the spring inside, attached to the original mass and the spring, will shift that frequency so that the whole cable doesn't go into that resonant condition. So they are applicable at specific frequencies. You can't change them to a broad frequencies. So that's how they are. Again, I can refer you to Daniel Inman's book on vibration analysis, which I use there. He talks more about the math part of it on designing the tuned absorbers to take care of that.
Thank you, sir. Thank you very much. Sir, is there any up to what fraction of TMD, what fraction of the original structure a TMD can have mass?
Up to what fraction? Yes. You don't want it to be as much as that. There are some ratios which give you, effective masses and all that. They're usually not, as high as the original mass. Okay, even a smaller masses with a spring are sufficient to take. The only danger those is not that. The more danger is when that smaller mass and spring starts resonating, the deflection of that mass and spring will be quite large. Okay, so there's got to be provision, clearances available below that machinery or wherever it attached for that free movement of that extra mass and spring, so that it doesn't go and impact somewhere else. And the spring stiffness should not be so poor that because of it going into resonance, it will break and tear away. And so those are other issues which are needed to be taken into account when designing tuned absorbers.
Okay, sir.
Uh,
Thank you, sir.
and in a way, adding damping is also what the effect on damping is also considered if you see the analysis over there. But it's desirable not to go that route because it distorts that overall effectiveness of it. It does not cause, in fact, effectively, you can make the original mass and spring to go almost to zero. This a well designed extra mass system is designed, you can make it perfectly zero because all the other thing is absorbed by the other fellow. But if you try to add on damping also, you will not, that effect is not exactly zero. You do see a smaller spike, if not as much as the original one. You will see some deflection on that. So some attention to be paid off is well covered by Daniel Inman in his textbook on vibration analysis.
Thank you, sir. Thank you very much. Yeah, any other
Okay.
questions? Any other questions from participants? Otherwise, we'll have a break for 5 minutes.
Good morning, sir. Am
And,
I audible?
yeah, yeah. Go
Yeah, we
ahead.
have one question, I guess. Yeah.
Yes, sir.
Identify yourself.
Sir, my name is Jayakumar. Sir, what is the difference between the curvature mode and operating deflection shape mode shape?
Between what modes?
Curvature mode shape and operating deflection mode shape.
I'm not sure what you say curvature mode shape. I never talked about curvature. There's nothing called a curvature mode shape.
But I read the many paper in which mention for the structure health monitoring, the curvature mode shape are very important. So I don't know what is the curvature mode shape.
I'm not sure about that. What we talked about is what's called a modal mode shape, mode shape at a particular resonant condition associated with the resonance, and the other is a operating deflection shape has got to do not necessarily at resonant condition, a condition at which a general modal pattern. That's the difference. I'm not sure, Dr. Prasad or Tej, did you ever hear about a curvature mode shape?
No, actually, I'm also not familiar with that, sir. But we do monitor the curvature of the mode shape for structural health monitoring. That is one
Ah,
more.
yeah, I get it. For taking effective steps where what the curvature is, it's more to do with the strain energy associated with the curvature, right? So if I'm doing applying damping treatments and all that, I would like to apply it at those portions where that curvature is existing rather than a tip of a sample where there is no curvature, where there's no strain energy. So maybe you're referring to that. I don't know. I've not heard those terms before, but perhaps it's differing to the overall uh, in a specified modal pattern there would be up and down curves, right? The curve is the the mode shape pattern is simulating curves, right? Sinusoidal curves and all that. Perhaps the literature, what that gentleman Jayakumar may have heard that term because of that. But typically, it's the modal pattern which does have curves associated with it, yes. And whereas a operating deflection shape need not have perfect curves like that. It is some sort of a general disturbance and movement involved of the overall structure. That is the closest explanation I can give you to the two different concepts.
Thank you, sir, for explanation. My next question, sir, I am also read about the power spectrum density for the signal analysis.
What is that? Okay, power spectral density.
Yes,
That's the amount of energy which is there, which is in the content. You can get from the overall spectrum pattern. You can compute this total power spectral density. That's got to do with the mobility function and all that. All those combined together, it will give you an overall figure how much of the energy is there in that content, and that's referred to as the power spectral density.
thank you, sir.
Mathematically, there are some relationships. I don't have them with me, but it gives you mathematically what it is, which is computed from the frequency response data as a separate parameter. And it's a good indicator of how much energy is taking place in that particular mode of vibration.
Thank you, sir. Thank you. And my next question, sir.
Mhm.
Sir, because I have written the all question, that's why I'm asking to you.
Sure.
Yes, sir. Why we take minus 3 dB below from the peak for the measure the damping by using the half power band method?
Okay, that is one of the reasons. The energy content is expected to be maximum for any curve, as again this all comes from the electrical engineering terminologies for a given signal, where the energy content would be the maximum, and the energy content is supposedly, from that knowledge, content is focused around, not at the peak of that frequency response function, but around at 3 dB levels. If you are using a linear scale, it is 0.707 of the peak. If you are
Yes, sir.
using a
Yes, sir.
log scale, which is normally used, it's a drop of about 3 dB levels. The width of that peak at that 3 dB, given in terms of frequency omega 2 on the right side, omega 1 on the left side of that 3 dB divided by omega n, that width of that in those terms gives you the loss factor at that energy, at that maximum energy. So that's why the concept of 3 dB, again, this comes from signal analysis of electrical strong signal content, and all that is focused around the so-called 3 decibel drop level. That's the real content level. So that's coming from there, and that's a apparently, when we look at it and verify it with other techniques like the logarithmic decrement, which takes place delta, as you call it, but in a free vibration decay, both of them have some between that and this. You can get the parameter called zeta, CO or C critical, delta or pi from log decrement will be equal to loss factor eta, uh, and which is equal to that 2 times zeta, which is that half power bandwidth point, omega 2 minus omega 1 divided by omega n, which is that the peak of the network, whatever the omegas are. If you do that math, it will give you those numbers. So that's how the estimation of the damping with that energy content is taking place for each peak. That's how this computed in the modal analysis.
Thank you, sir. Thank you so much, sir.
Okay.
Thank you. Professor Martina can proceed for a break, sir. I have sent you an email. If you could check it before the next session begins. Thank you, sir.
Okay, let me see. Okay, thanks.
Okay, now we have break for 5 minutes and we'll get back here.
Right?
Sir.
Yeah, the title is fine. Only one thing
Yes,
is,
sir.
one thing you said 9 o'clock your time.
So just a second, sir. The schedule for tomorrow actually it will start before actually the lecture is at 9 o'clock India time. But then we'd like you to log in at around 8:15 or so, sir, to finish the administrative things.
8:50.
8:15.
Oh,
8:30 is also fine, sir. Half an hour before that, so that we can finish some of our administrative things. I'll call you at that time, sir.
okay. What time should I come on? 8:30 your time, right?
8:30 morning time, sir. India time.
Okay, then 9 my time. I'll come on
Yes.
9 at
And
least.
the lecture will start at 9 o'clock.
Your time 9 o'clock.
Yes, sir.
No.
So 8:15, 8:30, you can if you can come online, sir, and then we can.
8:30 for you, which is 9 for me. Okay.
Yes, sir. Yes, sir.
9 a.m. to log on. Log on. Actual lecture will start 9:30. It's 9 o'clock your time. Okay.
Yes, sir.
Okay. Only one thing is this is for other outside people and all that, right? In institute engineers, I cannot put that as a PDF file or anything of my seminar. So whatever they have to listen, and if you guys record, it's up to you. But
Yes, sir. Definitely.
yeah, because it's based on some ongoing work here with the.
Understood. Understood.
So don't expect a PDF. Anybody asks those, say no. I'm sorry.
Of
Okay.
course. Of course.
Okay, you guys
Yes.
record, that's up to you, but I'm not, it should not be because there are outside other people and all that.
Understood. Understood.
Okay, that's fine, no problem. So I log on instead of like nowadays 8:30, I'm logging on every time. Tomorrow I
So
log
you
on.
can log in about 15 minutes ahead of time, sir.
Okay, all right.
8:15, 8:30, 8:15 or so, and then we'll finish some of the administrative these things.
Okay. All right. So there's nothing else in the morning tomorrow on day 5?
Sir,
For the students, there's nothing else on day 5?
there is nothing for the students. The course actually today afternoon. By today, in the second session, we'll be having their quiz exam, and so that takes care of the course aspect of it.
Okay.
And the students can also log in, join in for the uh, the ongoing research at the international, the uh, university
You
lecture.
encourage them to do it because there's a lot of interesting things we cover over there. Okay.
Yes, sir. Yes, sir.
Lot,
And
lot
lot
more
of
than vibrations.
yes, lot of students from NIT Warangal will also be joining in.
Okay.
So this will be not just those who have registered for the course.
Okay, yeah. Fine.
Yes.
All right, shall I proceed?
Yes, sir.
All right, folks, again, I think I winded up all the whatever knowledge I can pass on to you over my years of experience and got the experience from other folks over here and all these companies and my help from my students. Today, I'll try to tie up some of these to some physical examples of work done elsewhere and at my university and some of my research, which involves using these techniques that we talked about. Under these case studies, one external case study was done for vibrations in a gantry crane. A gantry cranes, you see all these shipping docks and all that, where something moves, all these loads are taken up and moved around and loads. So the problem was very heavy vibrations were occurring in the crane's gantry structure during operation. Okay, it was observed some very high vibration. The production management were in a great dilemma. A production stoppage for investigation and remedial action would be very costly, while a breakdown, if it is left alone, those vibrations are not rectified, the whole gantry will collapse. That's even worse, right? So they have to identify the source first of all. Just like we said, what are the strokes? Is it a natural resonance excitation or something else is causing this to peak at that point? So what's going on? So that's important to check systematically. The vibrations were only present when a particular winch unit was involved in hoisting the operation. One particular, there are several winches. All these are there moving. One of them, so it was found. From a few vibration measurements, the source was easily identified as the gearbox in that particular winch unit. Maybe this one, let's say. Spectrum analysis of measurement, generalized response measurements only. Okay, response measurements of the gains. This thing was found that a predominant vibration frequency was at this so-called 11 hertz, predominantly showing up. This frequency was in turn traced to the intermediate gear wheel corresponding to its rotational frequency. So rotational frequency they identified is all you can check, inside gear wheels. One of them was causing this peaking over there. Okay, but then problem identification. Now what you face with what the force levels that is generated by the gearbox too high, or was it a very small normal force amplitude which is causing a resonance in the structure? Is it that realistically because of that, or some other resonant condition of the whole structure, or some other small excitation force of something moving around somewhere else? So they are separate. To determine the answer, a driving point mobility measurement was made at the shaft, right at the shaft. A mobility measurement of this was made. Driving point, okay, pick up an accelerometer and whatever device and excitation at that point. Excitation by a large impactor and the top of the gearbox made the measurement both fast and easy. Okay, a driving point measurement right there. The FRF showed no resonance at the observed vibration. When they did this is the this is the this is the operating pattern which is causing when the gearbox is doing this sort of a pattern. But when they did a mode driving point, not complete modal analysis, not needed, a driving point measurement with a pickup transducer and an impactor at the point, they did not find a structural resonance over here. Okay, and the source was diagnosed to be the FRS showed no resonance at the frequency, and the source was diagnosed to be a forced vibration due to the rotating unbalance. So it's not because of a natural frequency of the structure. Any unbalance, remember, a small this thing which is causes a force and that causes a large unbalance. So determination of the unbalanced forces, a straightforward technique was applied to determine the mass unbalance, treating the shaft bearing as a single output, we can rewrite a linear model, force is equal to x over del. This was solved for the magnitudes at the frequency of 11 hertz. The unbalanced force magnitude was found to be 8.29 kilonewton point, I believe this is. A further calculation showed that this is equal to a mass moment of 1.74 kilogram meters, an eccentric mass, which always created this. So what was the solution? Now it is not structurally, they did not make any changes to the whole thing. Resonant condition, it's not, see, resonant peaks are more somewhere here, somewhere here, somewhere here, here. These are the resonance. So balance sheet shop was alerted. Production work was planned to proceed without crane operations during one working shift. The gearbox was dismantled, gear wheel transported to a balancing shop. Everything was remounted and ready for trouble-free operation within 8 hours. An interesting point is that although the assumption of a single input, single output model is coarse, the predicted mass moment of the unbalance was almost exact. It had been caused by a small fracture discharging a piece of the casting. The weight of the fragment was 3.3 kg, small, and its center of gravity was 0.53 meters. And we can do the calculations of unbalanced force of unbalanced mass times the acceleration r omega square, okay, and all these will give you how much and all that. So the small eccentric braking and all that. So again, this is to distinguish between is it because, like we said, those steps involved in it, is it an overall structural resonances, or is it a large force caused by this unbalance causing it? So you have to break it up, take a good look at that. Now I come to some of the type of work I do a lot in trying to find out how to reduce vibrations and things like that, and on structures, and improve some use so-called viscoelastic damping lead treatments. Just viscoelastic materials can be used as dampers, freely applied. Most of this is done quite often when you open your engine blocks and all that. Around those, they put some of these thick layers of it freely, free, unconstrained. But there is also called a concept called constrained layer viscoelastic damping treatment. What is that? What does that do? The energy absorption after compared for a single damping layer left. Suppose you apply a free damping layer without any thing on top of a structure. This is the base plate which we are trying to reduce the vibration. Excuse me. And a constrained layer damping is on top of this layer. There's a thin metallic foil attached. It's stiff enough, not thin, but thick enough and stiff enough, so that it creates, when this plate vibrates, which is a damping layer plus a metal. This foil constrains the viscoelastic damping layer, which is in the middle, and makes it deform and shear, absorbing more energy than longitudinal vibration of a single layer. Now, damping in viscoelastic materials or fluids and all that is provided by shear. Any deformation, the shearing deformations will create more energy dissipation than either a longitudinal or flexural type, axial up and down movements. Okay, that's the very nature, shear deformation. Somehow, if you force it, what we are talking about, the gentleman Ajay Kumar raised a question about a curvature. Remember, curvature in more shapes there will be a curve. The base plate, when it starts bending in this fashion, a curvature is formed like this. Okay. Now, if you see, you applied a damping layer on top of this, this creates a longitudinal deformation only, whereas if the constrained layer is on top of it, it creates a shear deformation also. So it allows all these elements to be sheared up to some point or all along. So this sort of a constrained layer damping, as opposed to applying as a free layer, provides a lot more energy for this vibrating thing to come down to zero very quickly. So that's the nature of what's called applied damping treatments, damping tapes, and they're all readily available. They're available all the time over the past 30 years. Uh, they have been applied. So 3M is a big player in this. Other companies do it too. Under resonant conditions, these are, if you realize there's a resonant condition, one particular mode shape is applying, you see the modal pattern, and you apply those points at maximum strain energy, not the point of maximum deflection, which is for a cantilever beam. The free end is maximum deflection. If we apply this, it's of no use. It's more nearer to the clamped end, which is more effective because strain energy is maximum. That's why modal analysis is key for plates and shells and all this, in order to know the modal pattern or the curvatures taking place, where so that you can apply the tapes appropriately. And how much tape to apply, just arbitrarily, not all over. So these are called constrained layered high damping tapes. So metal constraining layer and a static mode and a vibrating structure, and under a vibrating mode. What is happening? A metal constraining layer such as aluminum foil is coated with what's called Scotch damp. It's a viscoelastic polymer. It's their trade brand. Some of these are self-adhesive. You can adhesively attach it to the structure easily, quickly, where others must be activated with heat. Various applications are there. Scotch damp polymers are composed of long chain-like molecules. This viscoelastic materials are made up of chain tangled together in random formation. Whenever they are moved dynamically, vibrational forces cause these formations to slip and slide against each other inside. Okay, the metal constraining layer increases the strain in the molecules, makes it larger, but constraining it, the movement, stresses and all this, as opposed to pure without that constraining, smaller longitudinal deflections. Okay, through the friction of molecule against molecule, Mechanical energy is converted into negligible heat, which is dissipated within the damping layer. So, so the energy is all dissipated off with effectively by that nature and creating that extra shear deformation. The viscoelastic property of Scotch damp polymers may be likened to an elastic band made of both rubber and putty. Suppose you had a band of that type. When you stretch a rubber band and then release it, immediately retracts to its original length. But what if that band was made of putty, pull putty, the thing which kids play with to mold and all that and things, playing putty thing. When you pull it, it absorbs energy when you pull and retains its extended shape. It won't come back quickly. It will slowly come back if you do. The viscoelastic material combines the property of this and this. That's why it's viscose and elastic part and viscous part. So it always returns to its original shape after being stressed, but does so slowly enough to oppose the next cycle of vibration. So that viscous nature and the elastic nature put together combines, allowing elastic movement, but then when the elastic movement goes the other direction, it opposes it because this thing is trying to come back and forth, some sort. That's the whole nature of this systems. The multi-temp, they create a lot of temperature because viscoelastic materials are by their very nature temperature and frequency dependent. Okay, the nature of best performance will be over a range of frequency or temperatures, not all over. So you got to be very careful in selecting the type. They make all these types viscoelastics are effective over specific temperature ranges. Peak damping effectiveness occurs at the middle of a particular polymer's range. A major 3M contribution to noise and vibration control technology is the development of family of polymers that offer excellent damping performance in temperatures ranges from 0 to 250 or minus 70 or 9. So wide range. You got to selectively choose and apply it. A single layer of polymer, if you have, with metal foil backing, or they make types with both of these and then attach to the structure, or multi-layer combination of various layers of versions with polymer and metal, varying thickness and types of metal and polymers are used. So there's a tremendous developments of this all over, and here, let me finish this. For broad effectiveness, we build products with multiple layers of viscoelastic material effective over different temperature and frequency ranges. In this example, ISD 830 is most of that particular temperatures from minus 50 to plus 25, while a different one, ISD 112, operates at this frequency. One layer is always operating in an optimum point on the temperature and frequency scale. So these things have been used just a selection of applications. Okay, the World Trade Center. Okay, you think 20,000 3M building dampers protect the World Trade Center, New York, from the flexing effects of disaster winds and reduce day-to-day maintenance. This at the base where when the thing flexes, okay, back and forth, and this side, whatever winds, although maximum deflection is here, the real strain energy content is focused in these regions on the columns and all these and these layers over here. So the damping layers are applicable where the maximum strain energy content is there. So you cannot take into letter, effectively where the maximum deflection is there in terms of a curvature, that's the effect, not a free. Doesn't so at this point there is no strain energy, right, in a cantilever beam. In the fundamental mode, suppose these are excited in the secondary mode, it's upside. Then applying at the maximum curvature that is taking place in this and not at the node point. Again, that's the importance of the node point. In the second mode, there will be a nodal point here when it vibrates this way. So going and arbitrarily applying some damping treatments has no effect because effectively those regions are not being subjected. So that's the idea. New York from flexing effects of disaster winds and reduce day-to-day maintenance costs such as cracked plaster. All these some treatments are applied and all this takes care of. Jet inlet vanes, all these inlet vanes, clamp condition and all that, they vibrate, okay, with the forcing frequency. So those have to be reduced. Engine inlet guide vanes on military aircraft are fatiguing after limited operation due to complex vibration problems. With the use of a unique custom damper, the vanes remained uncracked after extended. So add-on damping treatments took care of that. What do you think your entire interior aircraft is between you and the outer skin? There's a lot of dampers applied in all over the skin layers over there. You may not see them, but how did they get? Which panels were near the engine? Which panels were vibrating maximum and modal patterns and all that are obtained, and pieces of these are applied all over interior. That reduces extra noise control in aircraft. Again, what is the noise control is coming from? From the vibratory panels. Apart from the sound of the engine, the operation, everything is vibrating. These are all flexing panels. Constrained layer damping panels, pre-cut adhesive back sections of Y370 directly to the aircraft skin. That's it. That damps out all that, kills that, and you won't feel it. Circuit boards, okay? Circuit boards, thin, flexible members, 3M damping materials applied to printed circuit boards protect delicate components from the effect of vibrational forces. Again, do you apply all over the board, or do you apply certain regions, certain frequencies which are likely to crack and bend? Modal analysis. If you do a modal analysis pattern and studies based on the boundary conditions, remember always a mode shape will change completely based on the type of boundary conditions are. Okay. So knowing the whole and dozen modal analysis will give you which particular frequencies are causing the problem, which creates which particular modal pattern, and wherever the strain energy and the curvatures are the maximum, they put a single layer or whatever based on the selection. Saw blades, all of your saw blades which operate when you see, you'll see a 3M constrained layer damper, okay, only helps reduce saw blade noise by up to 15 decibels, but also provides a smoother cut by reducing the vibration level. Vibrating this way, that way, in that region, if it is put, you get a clean cut within the blade itself. Without that, you would have gone completely off. Sound also reduced by that movement. Other applications constrained are in the process lot, including materials for industrial noise, architectural process, valve covers. Valve covers, 3M constraint is emerging important technique to help comply with truck pass-by noise regulations. So valve covers and all that, they create a lot of noise when moving. So they have developed for valve covers, brackets, oil pans, other parts of diesel engines, all of them have intense applications of this. So constrained layer damping treatments and then application, especially in aircraft structure, weight is a critical component. So you can't arbitrarily put on 2 layers, 3 layers and all that just like that to increase. So weight is extremely critical. So they try to choose the effective point, reduced weight and greatest effectiveness. Now, my own work during my dissertation work on PhD work involved using this vibration viscoelastic damping tapes for my work, and it involved because helicopter rotor blades in this country were being originally they used to be made with metallic aluminum and all that and things like that, which have their own issues of breakage and crackage and fatigue. So they replaced them with composite blades. All right, and even then, even with the composite blades, they were also having serious issues of a failure with fatigue cycles and all that. So they had to come out with a way. They found out why not we introduce these tapes, apply these tapes on top of the rotor blades in a proper fashion at an appropriate frequency, whatever is bothering that frequency range of interest. So we had to come out with some models to simulate the rotor blade as a cantilever beam, and then study about on the base material, choose on the base material. I think the base material will choose as the glass epoxy base structure, composite glass epoxy base structure. So on that, whatever they were using glass epoxy, they gave us some information. US Air Force, this is the US Air Force grant for helicopter rotor blades. Then we have to see again, you can't go on complete helicopter blade apply the tape. Well, you can, but then you add to the mass and is it really effective all over and all that. So we have to study for separate modes which one is effective. So we studied for the mode 1. We did a vibration experiments, mode shapes and all that, studied the mode and impacted and got the loss factor, which is a measure of the damping, and got the ratio with a tape and without a tape, untaped, ratio of that. And we found that based on the tape length to beam length, based on how much you apply and where you apply and all that, all play a role, okay, ratios and all that, okay, and the increases, tape free at the root. Suppose the applied tape is completely free and that up to the length, and also if you fix the tape inside, making it extra constraint, we saw the loss factor to shoot tremendously. Extremely high damping was provided by doing this. So there are a lot of increase in damping. Usually add or any damping, if you add, you have a tendency to lose the stiffness. That's the very nature of thing, that high damping is low stiffness is high damping for typical materials and all that. The goal is to not lose too much stiffness, but have that additional damping provided. So this whole exercise was done to do all that, and then it was modeled with the finite element model. The guy there who did along with me PhD, he's the one who went off and joined 3M company and worked for them to optimize the applications and all that, while I landed up in academia and all that for the 30 years. He's done pretty well and all that. So that's the idea, folks. Again, in this mode, best region would be at the base region, effectively first mode. Second mode, well, you got to be away. Somewhere here, application would kill the second mode of the rotor blade. And the third mode, well, at this point and this point of the cantilever, not near the node point or free end. Just putting something at the free end would not help. It will not stress the element in the center with strain energy created. Strain energy has to be created for that those molecules and the entanglements to move back and forth and all that effectiveness. So again, I told you, we study the impact hammer and get the excitation, we study the peak. If it was a tape beam length is 0, there's no tape applied, there's a resonant frequency of 135 hertz, and the damping was 0.004 with that half power bandwidth. For applying up to 0.2 of the tape length, okay, of the total length, then you see the same peak. Redid the test. It increased the frequency also because of the stiffening of that little bit and mass and ratio of the two. It increased and also improved the damping by how much quantity? You see that? Quite a lot, okay? 0.004 point. And immediately you notice that by that bandwidth increasing. You see that band? This is the half power bandwidth points go up as opposed to the half power points here. And if your entire tape was completely filled all across, well, you get a fantastic increased stiffness is increased and loss factor is also significantly improved. But is that really good idea? Is that really necessary? Because you add a lot of mass, right? The whole thing. So the idea is to know which frequencies are the troublesome ones, and modal analysis of those patterns are studied. And if you apply it at those regions, that was the recommendation. But it was not simply that easy and dry. The trouble is, remember, when a helicopter, this is on a static condition, okay? They'll always, helicopter wings will be down. When they start operating, the centrifugal forces of the wings will create axial movement of this, and what effect that has had to be simulated in the lab also, and under those conditions how these tapes had to be applied. Oh, it was quite a rigorous job, and that's where the finite element modeling showed that movement of this and strain energy and all that, what affected all that, and all those had to be taken account. So this is an example of how modal analysis and application of these so-called constrained layer damping treatments are applied in real life to try and offset these things, okay? And there's a lot of work I do over the years has been using the impulse frequency response vibration technique as opposed to impulse time response. The impulse frequency response is what we have been dealing about, response to an input impulse force using an impulse hammer technique for evaluating the modulus, the dynamic modulus, not static modulus, and the damping of a new class of materials which has come recently called supercomposite laminates. What is that? That's a company called Boston Materials here in the US has developed a material in between two layers of a, they introduced what are called Z-axis milled fibers between the thing, okay, between the layers, carbon fibers, which have a, effective, very, very effective in trying to reduce the shear effect which takes place in composite. Most of them get shear and delamination with one of the dangerous modes. So by growing them, they grow them on top of this and introduce. So we wanted to test those to try and see what effect those laminates have apart from their modulus or anything. So we studied some supercomposite laminate with a base layer, 16 plies of a pure laminate without these, and then these things grown on them. And the idea why we took so many is we wanted to not change the weight per unit thing was a requirement. So we overkilled it actually. We put a lot more than necessary, but not. But anyway, we took both of them and we cut samples from the base, this thing 3 each, and cut samples from the super composite laminates. And SEM picture shows you some of the laminate configurations and all that. And we try to maintain the volume as much aerial density as called, because that's, you don't want to add on too much. You can like add on viscoelastic treatment, you can add up and build it and throw a lot of damper and achieve it. But structures which are lightweight, aerospace and all that, they won't accept it. You got to not pay attention to the weight. So we did in a digital signal analyzer, we hung it in a cantilever pit, put an accelerometer. This is not a modal analysis. You don't know the modal pattern for this, but we wanted to study, impact it here and get the frequency response function. The moment we impact it, we got for the base layer, you see the frequencies, sharp peaks and all that. And the same one, if it was done on replaced it with the super composite layer, this is the layer for the super composite laminate. So it shows that yes, that super composite laminate dropped in stiffness, but also the bandwidth of this increased for each of these modes. If you see in this example over here, so you can take the resonant frequency and fit it into a differential equation and form a closed form solution. And these are all things which we record in our my dissertation and all that, and everything. These are out there in literature. All my papers describe how to get this. The resonant frequency, the length of the cantilever, the mass density, the cross-sectional area, and the eigenvalue and the area moment of inertia, all put into this for the fundamental mode will give you the modulus, dynamic modulus at that mode. If you want to get the second modes, this thing, the eigenvalue will change and the second mode frequency is fitted in and length is the same in area moment. So for all those, you can get a modulus, dynamic modulus and all that. And you can measure the damping. Loss factor is damping ratio zeta twice. We talk in terms of loss factor. The industry talks in terms of damping ratio zeta. And all these you see. So essentially what we found by the dynamic flexural modulus, loss modulus is simply product of this and this. Okay, that is the loss, energy dissipated, modulus dissipated. This is the stored energy. So basically it was found that the whole exercise found that 3 samples average, you see all the modulus is there, and this is the loss factor damping. So by introducing them that many layers, later on we realized it's not necessary because you lose a lot of stiffness by weakening these layers. So yes, it resulted in a loss. Resonant frequency of the beams is around 74. We focused on fundamental mode, most important. Resonant frequency of the supercomposite drop, which obviously would result in a drop in the modulus. You see that when fitted in this equation. An experimental row showed that by replacing 50% of the woven carbon fabric in the control panel with this milled carbon fibers in Z direction, dynamic frictional modulus reduced by 25-30%, which is a bit high. You don't want that much loss, but then parallelly increase the damping by 25-30%. Increasing the damping by 5 to 10% itself, 10, 15 is a good thing, because some of these undergo vibration. And the real kicker for this is how they improve in low velocity impact, which we are doing the tests and all that. They showed some improvement. The Z-axis fibers helped in low velocity impact test. And the other tests are in Hopkinson bar, high strain rate impacts, which I'll talk about and all that. How well these help that. And under a blast situation, that's the key. Under a blast and shock loading, which I talked about, those are all going on currently under investigations and all that. Okay, so now I'll show you a few videos of some of the work. Let's see. And some of my talk on the tomorrow, if you are present, it will show some of the blast and work and blast tube, how these samples are subjected to blast and high strain rate loading and all that. And so let me see where my videos are. Okay, I hope these things will play. Sometimes they are a bit. So we have this setup in our lab on. Let me show you the lumper parameter model. Okay, can you see my screen, Tej?
Yes, sir, it's visible.
Right. Okay. Let me. Wait. Okay, this is in our lab. We make the students do a single degree of freedom system. We have a 3 degree, up to 3 masses, springs, and damper can be moved wherever you want. You see this, we subjected to a forcing frequency. We theoretically, students calculate the mass, the stiffness of the spring, all known data, and calculate the natural frequency and force this generator to force that. So you see, in a fundamental mode, this is straightforward, right? Back and forth, exactly whatever we calculated. You see the spring mass, then they change the spring, they change the mass, they add mass, delete, all and study a single degree. Then they collect it, attach it to 2 masses. Then they attach it to 3 masses. Then they do a free damper. This is the air damper. There's the air cylinder, piston inside. And if then this is collected to this in parallel, it acts as a damper. Then they study the effect of this with the damping and see that frequency doesn't change, but a little bit of the peaks and all that chip. So this is single degree. So let me show you the 2 degree. I think we captured up to 2. I didn't have the third one with me here. So if you do the same thing in the 2 degree of freedom system, you see 2 masses connected. This is the first mode. They calculate theoretically using mathematical formulations and all that simple and excited at that frequency force. Then they see both lumped masses are going in unison, right? For this lumped mass. Now the same in the second degree, forcing frequency, second degree, should be marked somewhere on the picture, second frequency. And when they move that, these two going in opposite direction. See that? At that frequency. Then they do the exercise, once damper here. I don't know, I think they provided 3, but mostly we do apply it to, then we 3 masses, up to 3 masses. Theoretically, using the equations and all that, our students calculate on all this. So it shows the frequency calculation, adding a damper, what effect it has, and what's the modal pattern of the 3 lump parameter systems. The other one, oops. Okay, this is the whole modal analysis we do we have a standard fixture with a T-plate attached. You can do the whole modal analysis on the whole, including this, but mostly students focus on using the cantilever portion of the plate, and they put an accelerometer somewhere in the region over there, then start doing a complete modal pattern with a hammer, get at each one of these points, they discretize, and this discretized thing is fed into the software unit. I think the model analysis software here we changed over the years. The older one is gone. Something more recently, we got a very good one. I don't remember the name. But after doing all the tap test and all that, and then all the data connected and analyzed, the feedback gives you the actual modal patterns shown on your software developed, the fundamental mode. You see that back and forth, it's supposed to be all the way. Fundamental mode, back and forth, back and forth, back and forth. I think I got it. It's around, where is that? Hertz. 72.9 hertz. The fundamental mode of the plate going back and forth. And then we have the fundamental twisting mode. Fundamental twisting mode at 392 hertz. Back and forth twisting around the central line. You see that? Around this line, back and forth movement. Those are node points. Those are where you don't want to attach your accelerometer. That's why somewhere in the ideal region we found that around this was that. So this is the fundamental twisting mode for the students who see that and visualize, and they get very excited seeing all this. Okay, this is the second bending mode at 628 hertz. First bending mode was 71 hertz. Pure bending. It's bending back and forth. There's a node point here. You see that? So anywhere in this here, a third bending. We captured one more, I think up to 3 or 4 more. So this is actual work done on a modal analysis, modal pattern completely. And these people sent us some vibrant technologies. I don't know whether this is the model you guys saw in your this thing shape. Is this the one, Tej, with that somebody showed?
It is not this detailed, sir. It was a different.
So this is done in a vibrant technology. The company which makes all this equipment, they conduct this on a model airplane, complete modal analysis, and show you at different hertz. This is a frequency of 27.9, then 33.8 hertz. You see something or the other is changing, right? Like that. All particular modes they captured. So the at the back tail end, at that frequency coincides with the forcing frequency and all that. At that, the second mode of that tail and some movements here. Fantastic job with triaxial accelerometers, because there are some out of plane movement, and this is again the wing with the forcing frequency of the flying coincides with this twisting mode frequency at 67 hertz. That's how the whole airplane will be going back and forth. If the aircraft pilot stopped the speed of that engine at that RPM and you are flying in it, you would be scared to death, right? At that. And this is a coupled mode of the second bending and twisting and all that. Now you see the out of plane movement of the center at this hertz. There's a frequency over there, movement over there, and back and forth. That one more there. So folks, that's the fun part of doing this whole thing carefully. It takes a lot of work, carefully acquiring the data from the accelerometer, triaxial accelerometer, and tapping. Not it's a model airplane that was built and done that for demonstrating and letting students know, hey, how much of fun this modal analysis is. What else do I have to show you? Okay, this another exercise they do, make them do is for a beam. You may be surprised. Your cross beams, I beams, and all that, all your civil engineering structures and all that. Oh, they do have a frequency, resonant frequency conditions. At those frequencies, they'll do that. And imagine what that would do to that structure. So if something is not taken care of. Okay, again, completely done using a triaxial accelerometer and roaming hammer technique and all that. And I think I have one more example, shaker excitation. This is one more thing we do in our lab here. We use a shaker setup. Tej knows all this. He has been involved with all this. So a forcing frequency of the shaker, when it coincides with the natural frequency of the beam in the cantilever beam, dual cantilever beam, this is the fundamental mode, first mode. Theoretically, we make them calculate this. It's easily doable. Boundary conditions and all that formulas are there. And we also have a stroboscope which matches when you know the frequency and match that frequency of the strobe light, you'll see this whole picture very nicely as if it's static. Slightly move the scope away from the forcing frequency, which I believe this one was around 670 hertz or something, then you will see this slowly extreme ends. So fundamental frequency oscillation. Forcing frequency coincided with this theoretically calculated one. So let's go to the second mode shape of the same one. You see, what do you see over here? What is this point? The rest is moving here and here, almost static. You can exactly capture that with the stroboscope light perfectly. We did it, but the lighting of that stroboscope frequency and the camera, this thing, something mismatched. We could not freeze frame it, but actually the students, we shut all the lights and we freeze frame it. So up to 3 modes. The next was the third mode we captured too. Again, exciter, BNK exciter. This is a hammer. The transducer in between. This is the stinger pushing on the. This is not the stinger. This is the physical movement to do that. Stinger is when you push on a mass of that type and all that, the reaction forces. So you guys can see that, right? Of the second mode and all that. So I believe. What's the time? I have no idea what the time is, but okay.
Yes, sir. So actually, it is 9:55 a.m. Our industry expert, Mr. Rajshekhar, is also here.
Okay.
Rajshekhar.
So
Good
mine
morning.
is done. Okay.
Good morning.
I'm done. Okay.
Good,
Hello.
good,
Good morning, everyone. It privilege to be addressing one of the NITs.
And let me introduce Professor Mantena, our international expert, sir. He is a expert and authority in experimental model analysis and composite materials. He is emeritus professor at the University of Mississippi, USA. And Mr. Rajshekhar Uchil is he's a senior management and he's a deputy general manager for the JOS company. Just wanted to give you a brief introduction before the formalities.
What's the name of the company?
Post engineering, we are the partners of rural and care in India for the last 75 years.
Yes. So, Dr. Ravi Prasad.
Hello,
Hello. Yes, sir.
Dr. Prabhakar. We are partners of rural and care in India
Oh, your partners is BNK? Okay.
for the last 75 years.
Okay.
So,
Very good.
in
Okay.
fact, it was a great pleasure seeing the 4810 shake.
I think your voice is getting cut off. You may want to adjust your sound system.
Hello, is it better now?
It's better now. Yes.
Okay, yeah. So I said it was a great pleasure to see the BNK 4810 shake.
Yeah, really, these are some of the older shakers we have about 20, 25 years in the lab, but they do very well. They've been doing, I'm more a big a fan of HP spectrum analyzers and all that rather than BNK. But the instrumentation and these shakers and all that, they're fantastic over the years. So, Tej, do we take a break or we're going to continue on with this now? Tej?
Thank you for your lecture, Professor Mantena. Thank you, sir.
Are we going to continue now with this seminar?
Yes, sir. Now I'll be introducing our industry expert,
Okay.
Mr. Rajshekhar Uchil, formally, and I'll just take over the sharing screen, sir. Thank you, Professor Mantena.
You're sharing, right? Because I'm not seeing anything on the screen. Okay.
Yes, sir. Now I'm about to share now, sir.
Okay.
So it's my pleasure and honor to introduce Mr. Rajshekhar Uchil, who is the who is a senior management and deputy general manager at JOS India, and he is a graduate of electronics and communication from REC Surathkal. He's a postgraduate in advanced management and marketing management from IGNOU. He is a very well experienced with more than 35 years of industry sales, marketing, business development, and he's specially focused in vibration and acoustic sensors, conditioning analysis, and calibration. And he's also has a lot of experience in process control, motion control, and he provides a lot of strategic advisory services and is presented a lot of papers in national international conferences. He's he's a fellow of the Council of Vibration Specialists. He's a life member of the Acoustical Society of India and member of Institute of Indian Engineers. He's a life member of the All India Management Association and a senior member of the board on education and research in aerospace. Also for the he's also TMD for the International Society of Automation. So I give you Mr. Rajshekhar Uchil. Good morning, sir.
Good morning, everyone. It is a really a great pleasure to be addressing NIT from where I also graduated from an NIT long back, which is Surat. I have been involved in this. Can you see the slide, sir? I have shared it.
Yes, sir. I can see your slides. If you can turn on your video also, that would be fine, sir.
Yeah, I'll try. One second, sir. First, I'll put the slide.
Right.
So I will. Now the slide is clear, sir?
Yes, sir, it's visible.
Yes, so I'll just turn on my camera also.
Thank you.
I've turned on the camera here, but
That is fine, sir. No worries.
okay. So good morning, everyone, and it is a great privilege to be addressing a very high level of technology experts here in model analysis. I just saw an initial presentation on the shakers, and it is really fantastic. So what I would really like to do is look at more on the instrumentation and applications and share some case studies. I have been involved in model analysis in India right from the early 80s. The largest systems that we put in India way back there at Vikram Sarabhai Space Center. This was for the 1/6 scaled down model of the Polar Satellite Launch Vehicle. And you can imagine, even at that time, we were talking of model analysis and FE correlation, matching this with the answers of Astran models. However, at that time, we were looking at the Lissajous figures on the oscilloscope, noting down the values and comparing it on a notebook with the Nastran value. All that has, tremendously changed and everything is better. However, the fundamentals of model, what it is, whether you are talking of experimental model analysis or model analysis, reflection shapes, fundamentals of instrumentation have not really changed over the years. Yes, you'll find that some of the instruments have got developed. So when accelerometers from cars has become ICP, has become wireless. But concept of model analysis, wherein what you are doing is measuring the output and response, seeing the dampings, seeing the mode shapes, all that has not changed. So, yes, is it okay now? I've adjusted the speaker again. Hello?
You are audible, sir.
Okay, right. So we will just go through some of the instruments that we have here. Yes, okay. So when we look at model analysis, you are looking at the entire chain here. So you have something which excites the structure. It is model exciters or hammers, depending on the size of the structure and depending on the force required. You could have various hammers which are used for PCBs to a large shaker for an entire aircraft or an automotive. The important thing when we are doing shaker selection analysis, and the difference between taking a shaker here and taking a shaker for endurance testing is that we are not talking of the entire load of the test on the shaker. If the test object, it could be a car, it could be a pen, or it could be a PCB, is normally in a free state. So it could be hanging by bungee rods, or it could be on an air cushion, or freely suspended. And therefore, the shaker force is just enough to excite the structure. Now, and depending on the number of shakers mounted on the structure, so let us say for a huge aeroplane, we are talking of even 8 or 10 shakers, or even on a large truck, these shakers force ratings are good enough to excite the entire structure. We then go on to the transducers, which is the accelerometers. Now, the accelerometers in this case, two important characteristics of the accelerometer have to be considered. A, that the weight of the accelerometer does not affect the loading of the structure, which means that as a thumb rule, the accelerometer should be less than 1/10 the weight of the structure. In the case of modal analysis, then you should look at the weight of maybe the 100, 200 accelerometers that you have mounted on top, and to ensure that even with all that total weight on the structure is not dampened. You also today have possibilities of using laser vibrometer, for example, which is non-contact. The advantage is non-contact. However, laser Doppler vibrometers are quite expensive compared to a normal accelerometer. You then have a data acquisition system which picks up this data, converts it from the time domain to the frequency domain, and then we do the FRF, and then you do the modal analysis and the correlation. So as you can say, this is the entire instrumentation chain. This is vendor neutral. It really doesn't matter what the items are, who the supplier is, but the system remains the same. But you are trying to see the physical properties of the structure. You are also trying to compare it later on with the FE data to see how close is your sorry practical data with the FE data. So you have small hammers, right from 1.6 grams to 5.4 kgs. So right from small PCBs to large plain structures for civil engineering. Many of these hammers will impact it.
Sir, there seems to be some disturbance in the audio, sir. Hello.
Yes. Now,
Sir.
hello.
Yeah, there is some disturbance in the audio, sir. Voice is breaking.
Yeah, I think. Yeah, is it better now? Hello.
Slightly better, sir.
Hello. Okay, okay. I think the sound got slight loose. So, okay. The advantage of the hammers, as I was saying, you change the impact, so the bandwidth, the impact shape, the duration. And the question is also the software has a facility for taking double hits. This is part of the software analysis that we do. Then you have a large amount of what we call as modal shakers. The advantage of modal shakers are low weight, high rigidity, precision, magnesium moving element, and a very high force to weight ratio. With tension wires, as you can see in the right hand side, you can also suspend the shaker so that if for example, you want to excite the stand excited. So you have stingers, trunnions, piano wires, DC static unit. You have the force transducer mounted at the end of the stinger to measure actual force on the structure. You also then have accelerometers, which normally in case of modal analysis should be very high sensitive, should have a very low noise, should have a very flat amplitude and phase response. We really do not require a very, very high frequency range for modals. So normally 3 kilohertz or 4 kilohertz is good enough. It's not like monitoring our accelerometers going up to 25, 30 kilohertz. You have a low weight to minimize the mass loading. You have 3D mounting possibilities, which means that if a triaxial, you can change the direction of the accelerometers very easily. You also have marking on the accelerometers for orientation. Many of these accelerometers today are what we call as TEDs, which means transducer electronic data sheet. The information about the transducer is available directly as part of the inside the transducer. So when you connect it to the data acquisition system, the data acquisition system reads the transducer part number, the serial number, and the sensitivity automatically. This avoids any manual errors in keying in the sensitivity. You can use the same transducer for a variety of applications. It's really depending on the interchangeability, temperature operations, EMI, RFI interference, mounting. But the accelerometers basically are all general purpose in most cases. So then you are looking at also different clips. Depending on the structure to be mounted, you have high temperature clips used in engines. You have a thick base used on pipes. You have a swivel base wherein it could be on curved surfaces. The spirit level also to check that the accelerometer is absolutely flat on the surface and the transverse sensitivity effect is minimized. So these are some of the things that we will go in. I'm not going. You also today have a transducer smart setup, which means that you can scan the transducer and directly put it from an iPhone into the software. So you do not look at all the hassles of keeping track of tables, making the notes, keeping track of the orientation, making notes of the degree of freedom information. All this is today available automatically when you scan the transducer and put it into the software. So there is a manual alignment between the test setup and the measurement software. All these errors eliminated when we are using new technologies like a smart setup. These are some of the new technologies. Many of you may be aware of these technologies. This is only a question of ease of use. As I said, these technologies do not obviate the technology in terms of the analysis. This only tries to make your life easier. So you scan the accelerometer with data matrix code, associate with the 2D labels. You can improve the lighting, take the information, and all this goes into your software. You can do it even without. You then look at the data acquisition system, and then you can see that the component ID, the node ID, the degree of freedom direction, the type of transducer, everything is picked up into the data acquisition system, including the serial number and the orientation. So this gives you an idea of how the data goes into the system. So as you can see, that TEDS number, when the accelerometer is TEDS, also then the sensitivity of the accelerometer is directly read into the system. The serial number is read, so that makes it for records purposes also very easy. So these are some videos, so I will skip that. So, are there any questions at this stage right now? So, sorry, the video got paused. One minute, sir. We'll just go back to where I was. Sorry for the slightness. We then look at data acquisition systems. Do not look at the specifications from a sales viewpoint. Look at the fact that what are the important characteristics that a data acquisition system should have. The question is expandability. If you are doing a system which can expand depending on the requirements from a small structure for a classroom to a large structure like aerospace, for example, where 100, 200 channels. We have systems in the aerospace industries both in India and abroad with 200 to 300 channels. Frequency ranges depending on the module or depending on the applications that you look at. In many cases, 25.6 kilohertz bandwidth of the system is more than enough. Dyna-X is something unique in manufacturers where data acquisition system automatically ranges itself for a wide range of applications. This becomes very important in non-repeatable phenomena. You could have 12 channels modules or 4 input, 2 input output modules. Interchangeable front panels are very good for connection because you could have a much easier connection. Say, for example, triaxial accelerometers where you could have a single connection coming to the data acquisition system. So these are examples of where we are looking at. So you have ability measurements, you have ODS analysis. The ODS analysis is used in all cases where you are looking at real world conditions and how the structure is operating. So it could be time, it could be spectral frequency or order based, run up or run down. This has been found extensive use when you are looking at, say, a pump on a ship, a motor on a ship, and you want to see how the body's vibration changes over the process. Remember that the modal analysis is really done on a static structure, the ODS is done on a running structure, and we are not looking at in modal properties, we are looking at the shape of the structures and how it changes over the time during the process. You have classical modal analysis, which is using either a hammer or a shaker. It could be either a single input, multiple output, or multiple input, multiple output excitation. You also have different modes of excitation. For example, step line measurement, or very accurate, sometimes a bit time consuming. Operational modal analysis, which is another technique a lot of people must be familiar with, which is essentially that you are not able to measure the excitation. So, for example, a plane flying in the air, you cannot measure the forces of the wind. You're going to measure only the responses. Civil engineering structure, if I'm measuring property of a TV tower, I do not know the wind forces, but I'm measuring only the response. In the case of a ship, again, excitation due to the sea is not measured, but I'm measuring only the responses. I have other techniques like normal mode tuning, structural dynamics modification. This is the next one is the finite element interface. As you can know, that in many cases, you also always do the finite element measurement of the structure in Nastran or ANSYS or Abacus, and look at how closely your theoretical measurements compare with your practical measurement. So as you can see in the screen, you have both these models directly visual. You can orient both these models in the same geometry and compare with your COMAC how close are these structures. Your model correlation gives you an idea how close is your practical measurements and your theoretical measurements. This is today's sort of final step in the model analysis. This could be done both for a classical model or an operational model. So this is just a quick glance of what instrumentation is all about. I will now go into some case studies where you could and a little more on classical model analysis and OMA. Please feel free to take any questions during the presentation. Interaction is always. Is the screen sharing on, sir? Dr. Tezeswi?
Yes, it is visible. It is visible, sir.
Okay,
Yes,
so,
sir.
so we will look at a little on the model analysis. So as I said, the model analysis is the creation of a mathematical model of the dynamic properties and behavior of the structure. You have analytical model analysis, which is based on FE modeling, and you have experimental model analysis based on the hammer or shaker excitation. Where you get on the FEA, the eigenvalue, the the model damping and the eigenvector. In the case of the hammer or shaker excitation, we look at the natural frequency, the model damping, and the mode shape. These could be either classical or operational. One of the most classical pictures is the Tacoma Bridge disaster, where the bridge went into resonance and broke. This is one of the most classical studies of the effect of resonance on civil structures, and therefore is really studied everywhere. Many of you would have had this video. If not, I will share the video separately. Today, a lot of this is changed. We would have gone back to our classrooms and we would have studied, where the army is told not to march in synchronization on the bridge, scattered about, do not jump together on structures where you might excite the resonance. And that is the reason. That is really what happened in this, where the wind excited the bridge into its resonance, leading to its break. So when you do classical modal analysis, you are extracting the modes, the inherent properties of the structure that determine the mass, stiffness, and damping. We control the boundary conditions, we control the excitation signals, we control the environmental conditions, and then depending on the type of excitation, it could be a random excitation, it could be a transient, it could be a sinusoidal. You obtain the natural frequency, the mode shape, and the mode damping. What does this help us? It tells us what is the structure's inherent dynamic properties and what changes may be done. You have these applications in the industry where you have model correlation, you have design verification, you have troubleshooting, a structural assembly analysis, simulation of what-if scenarios, structural health monitoring. So this is just an example in a very large truck, 3 shakers, 330 accelerometers measured. These are all practical. So these are mathematical calculations. I will not go into explanation of these because these are available in the data sheets. But these are just mathematical algorithms available in different software for the calculation purposes. The PMIF, normal mode indicator, complex mode indicator, each of these are mathematical calculations developed by various vendors to give better information on this. So you have single degree of freedom curve fitters, you have multiple degree of freedom curve fitters. The idea is, depending on the type of material, depending on how close your nodes are, we will have to use different mathematical techniques, and these are all techniques to separate nodes. So you have the reference frequency, RFPZ, all of the alias-free polyreference. All of these are techniques developed by various companies for improving the calculations. You could have the mode shape animation, which is side by side, top bottom overlaid. You could have the complexity plot. You are synthesizing these plots, the automac and chromac, crossmac for the model assurance criterions. All these can be separated. Then you can look at the complete system here, where you could have the stabilization diagram, the curve fitting, automatically reported Word or Excel, integration with ideas or other software, tree correlation. Then we went back to what we looked at this. This is another technique we look at, which is operational model analysis, which is by response testing only. We estimate the frequency domain decomposition, the stochastic subspace identification, and the structural health monitoring. What happens or where is it used? You could use a large windmill, for example, which is where the very common places where this technique has been used, where you cannot excite it, but you have to see how the winds respond, especially at very high wind speeds. You cannot measure the excitation. It is difficult to reproduce the boundary conditions, static loads, effect of the air, associated mass, and especially in fluids like in underwater structures or in the air. It is very difficult to measure any of the forces. And then we look at operational model analysis or SHM for this. So this, for example, on a grid with 33 transducers and 5 references, where operational model analysis is calculated to check the algorithms. You have a signal processing, you have the model fit, and then you have different ranging from very simple signal processing like frequency domain decomposition to advanced techniques like advanced EFDT, curve fitting, stochastic identification, UPC merge. All of these finally give you the natural frequency, the damping, and the mode shape. These are all mathematical equations. In situ, in natural environment, here the natural input is used, ambient or self-generated vibrations. No measurement of the input forces. You could also do ODS from here. So it evolved from civil engineering on bridges, towers, wind turbines. We have also now case studies of this being done in the aerospace industry. In fact, HAL is doing it on the aircraft. We also have examples of this being done in the Indian Navy for pumps, motors mounted on the ships where they look at both OMA and TS. So this is just a glance on some of the applications. I'd like to take some questions now before we go on to some of the examples of case studies. Any questions, please, sir? Hello.
Questions from the participants?
Hello, sir. Good
Yes,
morning.
sir. Good morning.
I'm Neeraj Yadav. Actually, I want to measure a soak on a gun barrel,
Yes.
approximately 20,000 G. So,
Okay.
is there any miniature sensor so that I can mount there?
Yeah, we have done similar measurements just a couple of months back in Pune on gunshot measurements. In these sort of techniques, you could have shock sensors which are 100,000 G mounted. And then what is important in such cases is you would use a technique called SRS, shock response synthesis, wherein it tells you what is the shock at that point on the gun barrel. I will try to show you an example of that software after this. But this is a very common technique used, and in fact, this has been used even in HAL for the missile launches from the aircraft to measure what will be the shock of the aircraft when the missile is launched from the aircraft or when the missile hits the aircraft.
Okay,
You
actually,
have shock. You have a software which can pick up this time domain and then do an SRS calculation of about 37 different parameters immediately.
yes, SRS I can plot, but we had only 1000 G sensor, so it got saturated because the soak was.
So there are two things that you would have to consider when you do such measurements. A, sensors which are meant for shock measurements. So there are sensors which are 70,000 G, 100,000 G shock sensors. Second, and as I showed you, one of the examples is that your data acquisition system has to have a very, very wide range so that right from a very simple seismic to the shock, data acquisition system is able to pick up this
Yes,
instantaneously without auto ranging. These are
data
two
acquisition is
important things.
capable to measure the soak.
Yeah, so your dynamic range, for example, when I say 160 dB dynamic range, I'm talking of the comparison between a human hair and Mount Everest. That is the sort of measurement that I can do absolutely simultaneously without any ranging on your DAS. That's one. The second is you could use shock accelerometers which could easily measure 100,000, yes, almost a million G,
But
and
the
at
thing
very high
is,
frequencies.
the thing is for those soak sensors, we have to do tapping and we mount like that. But on the barrel, we have to either means through the X60 bond, we have to mount.
All the shock sensors regrettably are with permanent studs. So because the thing is your mounting affects very much the response of the structure.
Yes, but there
If you
is,
mount plastic or magnet at such high G levels, the sensor will just go off from the barrel.
yes,
You would
that's
have to
the
have
problem.
some sort of a facility wherein you can do a tapping shock sensor, and this is used by the defense departments all over the world extensively.
Yes, we have one
The
lab of sensory, but they need some tapping things, and there is no.
tapping is important. The very important thing in accelerometers is your mounting characteristic. You could have hold the accelerometer in the hand. You could put it with a plastic adhesive. You could put it with a magnet, or you could put it with a stud mounting. Now, the advantage of a stud mounting is the largest dynamic range and frequency that it gives.
Yes, sir, yes, sir.
Most of the other sensors mounting techniques literally fail at bad conditions like what you mentioned.
Yes,
In
sir.
fact, even in HAL, what they do is you have the tapping already permanently done there. Tap the
But
accelerometer during the test and do the run.
okay,
You can send me your mail. I can send you some examples on this later on also. Which you are from
okay.
the college, sir, or from industry?
I'm working in DRDO.
Okay. So, in fact, sir, we have done this SRS measurements at Pune recently with one of the private companies. Or we have done SRS extensively, as I said, even with ADA and ADE, the missile launch analysis of the LCA.
Okay, sir.
Hmm.
I will send you the mail.
Yes. So this is just an example of a case study on NASA on new electrical powered aircraft, the NASA X-57, where it has used a very large system with 200. So you, as you can say, you have the Bungi characterization to ensure that the Bungi cord would hold the test, so that the frequency response is not disturbed. Then you put it on the one tier so that aircraft is in a free stage, and then a very large model analysis is done. These are giving the audience an example of actual applications of model analysis in very large structures. So we are talking of accelerometers at 127 locations, 300 degrees of freedom, 300 channel data acquisition system. As you can see, huge bunches of cables all over. For your information, similar systems are there in HAL Bangalore also. So there is 256 channel systems in HAL aircraft, in HAL helicopters, NAL. We have been associated with some of them. So this, for example, as you can see, what is the objective of the setup? Where is the excitation? What is the excitation type? What is the cockpit control? What is the cockpit? And it just gives an example of. You can see very clearly the GVT results shows airplane modes that did not show up in the text or FEM results. And therefore, now you know that there are modes which have got missed during the FEA, which has come out during the actual GVT process. So this is just an example of data that is done during a test study. I will also give you another example of a satellite testing. This is in Brazil. Again, very large satellites, 324 channel systems are doing measurements. Again, similar systems are in India, in ISRO, SAC, SHAR. So, an example of a satellite inside an acoustic facility. Those of you who have worked in the aerospace facility would have seen such large rooms in NAL, in ISRO, in RCI Imarat, which is acoustic factory. This is one of the very unique excitations where you have huge horns on the walls of this room. This room is entirely reverberation, and sizes in India range between 1100 and 1300 cubic meters. You have a horn which excites the entire structure at around 150 decibels, maybe for about 10 or 15 seconds. This is the type of noise that the satellite is subjected to when it is launched. So these measurements are done here. In fact, believe me, 15 years back or 20 years back when this measurement started, there was a failure observed on our augmented satellite launch vehicle solar panel. So this gives an idea to the scientists what happens in acoustically induced. Now you have these large facilities in NAL and in ISRO Bangalore, which are 1100 and 1300 cubic meters. In fact, the ISRO one is even with the nitrogen atmosphere for measuring the response of these structures. And then you have the large checkers on the satellite cables with monitors to see all the data at simultaneous vibration test control, the acquisition, all this can be seen simultaneously. From an electronics viewpoint, look at it that you are 320 channels at 131 kilohertz sampling per channel will produce a file of 96 dB. So therefore, this is the sort of data streaming that comes out. So your computers have to be capable of writing this data. Today you have computers with mirroring configuration so that data and the OS are in separate files and are written automatically and no loss of data occurs. This is actual. Those who are students, especially who are not aware, these are actual conditions that measurements that we have seen, we have done. And this is the sort of power expected from the data acquisition systems. You can see the amount of control rooms here. The remote monitoring, post-processing, real-time data, 324 channels of data looking at transient, phantom, swept line, all the analysis going on in real time and post-processing. Immediately when the satellite launch occurs, people look at the data in real time. As soon as the launch is over, the processing takes over and gives a report immediately, so that in case of any failures, you know what could be the problems. Complete control console. You can see all the parameters on the right hand side. You can see the time data. You can see the frequency of all the channels being showed. It could be the FFT, it could be in the CPB. So you have a setup, you have a calibration, you have a recording which goes parallelly, post processing, archiving, reporting. So depending on who access what, all the channels can be seen simultaneously. So these are just examples of the systems, network switches, display units, large monitors, where data can be seen. Very, very important. So these are some of the examples of real world applications of this. Any other questions on these applications, sir? The idea was to give from an industry perspective, because I see the syllabus and I've seen the faculty, and you have. For the audience, believe me, you will not get a faculty of these levels at any time. You have a tremendous amount of knowledge coming on this, on people who have worked for years and years on all types of modal analysis. So my idea, more from the industry viewpoint, was more to talk on industrial applications, because many people may not have seen such applications and they want to know where modal analysis is actually used. Any questions, sir?
Hello, sir. I'm Neeraj.
Yes, yes, yes.
Do you have progressive wave tube facility for the acoustic?
I'm sorry?
Progressive, like reverberation, we are doing acoustic testing now. So there is
Yes.
progressive wave tube facility.
We have only the impedance wave tubes which are used for material testing, used both in the space and defense industry, NSTL, VSSC, both for studying the measuring the acoustic impedance of the materials, absorption and transmission loss.
So like the progressive wave tube na, if we want like more dB, 170 dB, like so we need some different facilities, because
No,
the
we
reverberation
don't have those type of tubes. We have only the standard impedance tubes, which is, as I said, used in both NSTL and VSSC.
so there is a limit na, like 160 dB, 158 dB.
This is not done at high pressure. In such cases, for example, NAL does in the facilities is put the material in actual conditions in the reverberation chamber at 150 dB, excite it as a panel, and look at the absorption and transmission loss on an entire panel. That
Okay.
is what the measurements they have done in NAL. I know that because I have been involved with the acoustic chamber in NAL from 85, 86.
Okay, one more doubt is there. Like I was measuring some transport measurement on the axle of the vehicle.
Yes.
So in one axis means the signals in the time history was only one side of the means mean axis.
Yes.
So what is the reason for that?
I'm not very clear. When you are doing transportation tests, you could have recording either on a single axis or on all the three axes.
All the
Measure
three
the
axis
data
axial.
and then look at the road trials, wherein you could take this recorded data and run it back in a shaker to test
Cross.
the sortability of the structure, which means that simulate in the lab sort of vibration that the test object have undergone on the road. So if you are saying loss of data, you would have to look at either the sensor or the data acquisition system to see where the loss of data could have occurred.
Yes, I want to know, is it due to the some phenomena happens, or it is due to the sensors means problem?
You should, one of the ways to really check it out is to use a field calibrator and check the sensor with cable before doing the test. after doing the test.
We did through the signal conditioning also, and we check after also the sensor was okay, but in like the data was for 20 second or means 60 second. So initially 20-30 second data was okay, and after also okay, but in between there was some one side only data.
I would, really, you would maybe look at 2 or 3 accelerometers mounted in different places in the structure and see whether it is a sensor problem or it is a cabling problem. Because data doesn't vanish. So it could
Yes.
happen that, the sensor went into saturation or something. But the ideal
No,
thing
no.
is to have 2 or 3 sensors close enough and look at all their data and see whether it is a problem with the sensor, the cable, or the DAS.
Okay.
So, I mean, it's very difficult for me to, just sit here and say what could be the problem, but these are things that you could look at. I mean, you could mount 2 sensors very close, and now run both of them to independent channels of the DAS, and then look at the data simultaneously and see whether any data is vanishing during the test.
Yes, in the coming we can do, but the same test we cannot repeat like we did in the cross country roads.
Yes, yes. I mean, so the reason is therefore you have to have, say, a redundancy in terms of recording, so that let us say one channel you have lost some data. You could look at the second channel and see whether my data is okay or not. That's the only
Yes,
thing
sir.
that you could, take care of such mistakes. I mean, I won't say mistakes, such happens because no sensor or data point system is infallible. Something may have happened. Maybe in a triaxial sensor, it could happen that one of the channels is not working. So you get another. You get data only on X and Y and not on Z. The data acquisition system ICP power may not be coming properly to all the 3 channels. Some sensors, triaxial sensors, which mandatorily require power for X, Y, and Z. If there is a problem in the DAS and one channel is not coming, the sensors don't work at all. So these are
If in
just
that,
examples.
if in all 3 direction we are getting the same things, it means sensor have problem.
It could have a sensor problem or the DAS problem. I would say check sensor, check cable, check DAS, all the 3 independently.
Okay, sir.
Because you don't know where the problem is. To assume, you put 2 sensors side by side, and then you see what the result is. So
Yes,
then
sir.
you say,
Yes.
okay, everything else being identical, the cable is okay, maybe the sensor is a problem, maybe the DAS is a problem. Look at the time data of 2 or 3 sensors mounted closely and then start investigating whether under identical conditions and identical sensors there is any issues.
Okay, okay, sir. Thank you so much.
Any further questions from the participants, please?
I'd be very happy to take even questions later on also. Dr. Tezeswi has my phone and email, so you could always collate and send your questions around. I could share some of these case studies also with him, which could be circulated. A lot of this information is in the public domain, so there's nothing really confidential about it, but it gives a good idea to people on application of modal analysis in industries.
So once again, thank you so much, sir, for sharing your tremendous real world experience and bringing certain practical issues to light as well. And I once again thank you for being with us today, and hopefully we'll continue this association in the future in terms of inviting you over for other workshops, as well as
I have been personally involved for the last many years with colleges in India on what is called as syllabus update. So,
I see.
try to match industry expectations with what is taught in the college.
Yeah, right. That would be very useful, sir. And
Yes.
we also do a lot of collaborative research with industries
Yeah.
from
We'll
NIT.
be very happy to connect you to other academicians also where we have worked extensively. For example, as I told Dr. Mohanty, IIT Kharagpur, Dr. Fatima, IIT Hyderabad, Dr. Munzal, IISc Bangalore. Many
Right.
of these professors, Dr. Jena, we have worked with many of these professors in the academics. They are well aware of our capabilities, and we could also connect with the industry.
Right.
Where industry is looking at partners to solve a lot of problems.
Yes, sir. So we do at NIT Warangal Department of Civil Engineering and also in Mechanical Engineering. There's a lot of active research ongoing in terms of structural dynamics and vibrations, respectively.
Fantastic. I would also send you details of a number of conferences internationally, including, I think, I sent you for the OMA conference also in Canada.
That is correct, sir. And you are also a member of the Council for Vibration.
Yes. I'm a life member of CVS. I'm also a life member of the Acoustical Society of India.
So I invite all the, I take this opportunity to inform all the participants that there is also something called the Council for Vibration Specialists, which is a very good forum and platform for interacting with industry specialists as well as, academic professionals. And I take, you are encouraged to sort of, become a member of that. So
It's really got a huge range of professionals of all the domains. The best advantage is the industry connect that you get out here also.
that is invaluable, sir. Yes. Yes. Thank you so much, sir, for sharing your time and spending your valuable time with us and sharing your vast experience as well.
It is my privilege, sir. If there's anything you or your colleagues or the people in the audience today, that we have a very large participation, I'd be very happy to share. Dr. Tezeswi, you have my phone number and email also. So, Doctor could be the nodal point for any communication.
Yes, sir. Definitely, we'll be passing this along to all the participants. Your contact information will be shared with all the participants.
I will at the end of the day share some of these case studies also, which you could circulate also.
That would be very beneficial, sir, so that because we are going to distribute these as part of the course material.
Yes.
The lectures
Studies
provided by the
that are shared are all in the public domain, so there is absolutely no issues in sharing it also.
Thank you so much, sir. That would be great. Yeah,
I will do that, sir.
So appreciate this time you have taken and spent with us. Thank you so much, sir, and we wish to have you once again in future. Thank you, sir.
Welcome, sir. Welcome, sir. Thank you very much.
Thank you so much, sir. Good day. So, participants, a general announcement to the participants. We will be taking a short break up till 11:30, and at which time all of you will be given a quiz, which is mandatory to attend at 11:30. So, we'll take a break up till 11:30. Thank you so much.
Right, sir. Thank you very much.
Thank you, sir.
Everyone.
Thank you,
It was
Rasi.
very interesting answering all the questions. Also, it was great privilege.
Yes, sir. It's our pleasure, sir. Thank you.